Welcome back to the Deep Dive, where we deliver the essential insights buried deep within the source material. Today, we are taking on a conflict that sits right at the heart of the modern tech sector. I'm talking about the often gaping chasm between academic computer science theory and the daily, gritty reality of professional software craftsmanship.
It's a huge topic, and this isn't just about what's in a university curriculum. It's about a fundamental failure in how the industry onboards and trains its newest people.
Exactly. Our sources offer this really powerful, almost scathing critique.
If they really do. They argue that while universities do a great job, an admirable job, with the science part, the algorithms, the data structures, all that.
The theory.
The theory, exactly.
Yeah.
But the industry has pretty much abdicated its responsibility to provide the necessary structure for discipline, for practice, and for genuine skill acquisition. So we're diving into why a formalized system of mentoring and a deep commitment to the ethos of craftsmanship are not optional extras.
They're absolutely essential.
They're essential for the future stability of software.
And we are starting with this one anecdote that just perfectly crystallizes the whole problem. It's a story that, when I first read it, it highlighted the systemic disconnect for me.
Oh, I know the one you mean.
The author recounts interviewing a young candidate, and she was pursuing a master's degree in computer science at a highly respected major university.
Top-tier program.
Right. And when asked, as part of the technical interview for the summer intern position, to actually, write some code, her response was just jaw-dropping.
She said flat out, I don't really write code.
I mean, can you imagine? I don't really write code.
It seems impossible, doesn't it? A master's degree in computer science and you don't write code. So the interviewer naturally is a bit stunned and probes a little deeper. He asks, which programming courses she had taken for her degree.
And the answer?
None. Not a single one. She hadn't taken any programming courses. She had successfully navigated one of the most intellectually demanding academic fields based entirely on theory, on mathematics, and these high-level design concepts.
But without ever having to sit down and actually produce working, demonstrable software.
It shows that this isn't just an isolated case. It's symptomatic of a much larger structural issue. It's a system, as the source puts it, that allows an individual to wiggle yourself through.
Right. You emerge with a diploma, a very impressive one, but without the core practical skills the industry is crying out for. You can master the abstract theory of computation, but completely miss the craft of turning it into reliable, functional code.
And that really underscores the tension, inherent in the university system. They are set up to teach computer science. They are not set up to teach computer engineering or computer craftsmanship.
And that disconnect is the basis for our whole deep dive today. The degrees of failure and the absolute necessity of finding other routes to competence, specifically through deep mentorship.
Yeah. And if that master student is sort of the symbol of the system's failure, the sources point to a really fascinating counter-observation.
This is the university paradox, right?
Yeah, that's it. The graduates who tend to disappoint in the industry, they often share one common characteristic. They had not taught themselves to program before they got to university.
Whereas the ones who flourish, who really get it.
Almost universally, they taught themselves to program before college. And they kept teaching themselves, sort of in spite of the formal education they were getting.
So the self-taught programmer, by necessity, has already bridged that gap between the abstract and the physical reality of the machine.
Exactly. University programs, they're excellent at the critical foundations, data structures, computational theory, complexity analysis. All that stuff is vital. But they rarely teach the messy, practical aspects.
Like version control or debugging a legacy system someone else wrote.
Or just collaborating on a massive code base, writing code that someone else can actually maintain a year from now. The curriculum is academically rigorous, but it's vocationally incomplete.
So the people who succeed are basically running their own parallel self-directed apprenticeship before they even set foot in an office.
That's a great way to put it.
So that just begs the question. If the formal system is so unreliable for producing skilled workers, how do we actually get those foundational skills?
We have to look at the proposed solution, which is the crucial role of effective mentoring. So let's dig into the author's personal history, which really illustrates how this skill acquisition often relies on these unconventional, sometimes accidental, early mentoring experiences.
These origin stories are so important. They show you the exact moment the light bulb turns on, that moment the abstract theory gets physically connected to a working machine. And that connection, That's the missing piece.
Okay, so let's start at the very beginning of that journey. We're talking about the author's first computer, the Digicomp I. He got it for his 12th birthday back in 1964.
Yeah, and we're not talking about a desktop computer here. This thing was small, plastic, and you could see everything working. It was designed to physically show you computer logic.
So what was it made of? It had 3 plastic flip-flops, which are just binary memory cells, and 6 plastic and gates. And by, manually arranging these parts, you could build a physical, working, 3-bit finite state machine. It was Boolean logic you could hold in your hands.
And programming it was just as physical, right?
Oh, yeah. It involved pushing these little tubes, basically short bits of soda straw, onto pegs that stuck out from the flip-flops. You were physically setting the state machine's transitions.
The manual it came with was a problem.
A huge problem. It was prescriptive. It told you where to put the tubes to get a certain result, but it gave you zero explanation as to why. So for a curious 12-year-old, this is just maddening. The machine was powerful, but it was locked.
And this is where the first mentor comes in. And it's not a person.
No, it's a document. After hours of just trying to figure it out, he sends $1 to the manual company for instructions on how to actually program the thing. And what he gets back is this simple 3-page treatise on Boolean algebra.
And that was the key.
It was everything, the elegance of it. I mean, it covered the basic concepts of factoring Boolean equations, the associative and distributive laws, and critically, De Morgan's theorem.
So suddenly all those frustrating plastic tubes and pegs.
They were connected to a system of pure abstract logic. The source describes the elegance of that 3-page document as just compelling. It was the conceptual framework that turned a toy into a real tool.
And the result was his very first program.
Mr. Patterson's computerized gate. He wrote the equations, he used the principles from that little manual to reduce them to their simplest form, and then he mapped that logic directly onto the tubes and pegs.
And it worked.
It worked. And the chill he felt, years later thinking about it, wasn't just satisfaction, it was the realization of intellectual power. He had used mathematics to bend physical reality. That ability to translate a theoretical idea into a working physical device, that's the soul of engineering discipline.
That experience just completely sets the stage for what comes next. So fast forward 3 years to high school, and the learning style shifts. It goes from self-directed manipulation to this intense observation and deduction. And the machine is the ECP-18.
The ECP-18 sounds like something out of a sci-fi movie from the 50s. He was 15 when this table-sized educational computer was wheeled into the math department.
The specs sound so vintage.
Oh, they are. A 15-bit word and 124 words of drum memory. And it wasn't quiet. It was a physical presence in the room.
The description in the source is amazing. It looked like an office desk with this marvelous control panel protruding like a battleship, just covered in lights and push buttons.
And the sound. When you powered it on, it made this whining noise like a jet aircraft taking off. That sound was the backdrop for his next big lesson in programming.
So he just sat there watching the technicians who were operating this beast.
Intensely watching them. They'd push sequences of buttons like deposit and run. The machine needed direct, low-level instruction. The buttons were grouped in 5 clusters of 3, so they were literally inputting octal digits in binary, pure, raw machine language.
And this is where the breakthrough happens, just from watching.
Just from watching and listening. The technicians would push a sequence like 1, 5, 2, 0, 4, and they'd mutter under their breath, store 204. Then they might load 213 into the accumulator.
And he picked up on that.
After just 10 minutes of this intense, quiet observation, the 15-year-old figured out the instruction set. The number sequence 15 meant store, the sequence 10 meant load, the rest were memory addresses on the drum.
He reverse-engineered the machine's language without a manual.
He did, which is just an incredible demonstration of engaged observation and pattern recognition. It's a skill we use all the time in software, right? Whether you're figuring out legacy code or just debugging from error patterns.
So this deduction leads to the next logical step for a curious teenager.
Sneaking and fiddling, he describes creeping into the math lab after school, living by that philosophy of asking for forgiveness, not permission.
And he actually gets it to work.
He figures out how to use the buttons to toggle in a tiny program, a simple routine to multiply the accumulator by 2 and add 1. And when it worked, that feeling was just visceral. He says, I was master of the universe.
The satisfaction must have been immense. But the real learning came a few days later.
Right, when he finally finds an instruction sheet with all the op codes, he was, pretty gratified to see he'd correctly figured out a lot of the instructions just by watching, but there was a huge gap in his knowledge.
A halt instruction.
The concept of a halt instruction had just never occurred to him. The HLT instruction was simply a word of all zeros, but he didn't realize you needed a formal command to stop the program's execution loop.
Which is such a perfect example of the limits of just learning by yourself by just fiddling.
Absolutely. He grasped the operational flow, but he missed a critical boundary condition that you need for, professional complete program design. This is why you need that formal knowledge. Even if it's just a 3-page guide to Boolean algebra, it gives you the whole framework that blind experimentation can miss.
It shows why you need those elders who know all the rules.
Exactly.
The sources also tell this great story about a non-mentor in this same environment. It was a teacher who was just desperately struggling with a program.
Yeah, he was trying to get it to type 2 numbers in decimal on the teletype that was attached to it, which for a machine of that vintage in machine language was not a trivial thing to do. You had to read the characters, convert them to binary, do the math, convert back to characters for output. It's a nightmare.
And the whole time the author is just
Watching every twitch, every muttered comment, learning at a furious pace, even as the teacher saw him as this nuisance just flittering around. The author saw the teacher put in a halt instruction and use it like a primitive breakpoint.
A way to stop the program and check the registers.
A technique the teacher had clearly just rediscovered out of sheer frustration, and the author absorbed that. The teacher eventually got it working. But the real takeaway is the power of that observational learning, even when the person you're learning from is ignoring you or is actively hostile.
It shows that professional values and problem-solving techniques can be transmitted just by being visible.
Exactly. It was an unconventional foundation, but a profound one. And these observational lessons were crucial, but they needed to be formalized. Which leads to all the other non-traditional mentors and the ultimate hard knock that really professionalized his career.
Right, we have this whole supporting cast. The kindly neighbor who brought home relays and an electric train transformer.
So he could build his own logic circuits?
The ham radio operator who showed him how to use a multimeter.
Bridging that gap between electrical theory and actually testing a signal.
And the office supply store owner who let him play with these really expensive DEC machines, the PDP-8 and PDP-10.
Giving him access to real-world, larger systems. It's all about exposure, access, and specific technical insight. But raw technical skill, as he learned, was not enough.
No. He found that out in 1976 when he got fired from his first job in factory automation.
That was the real wake-up call. He was technically brilliant, but he had zero professional discipline. He couldn't integrate his skill into a business context.
He broke the system on a Friday night, right?
Yeah, just totally focused on the technical puzzle and completely forgot there's a massive demo for clients on Monday morning. He shows up late to an office full of angry, staring faces.
Then they gave him a warning.
A formal warning letter to shape up, which he just ignored. And so eventually he was terminated. The technical skill was there, but the professional maturity, the commitment to deadlines, to business goals, to code stability, it just wasn't.
But the silver lining here was Jim Carlin, a BAL programmer. Was what they yell again.
Basic assembly language. And Jim Carlin was the one who provided that foundational mentorship in true craftsmanship.
He didn't teach him a new algorithm, though. He taught him something else.
He taught him discipline, he taught him how to debug core dumps, and for anyone who hasn't had that pleasure, a core dump is a snapshot of the computer's memory and all its registers at the exact moment a program crashes.
So debugging one forces you to be incredibly meticulous.
Relentlessly logical and disciplined. You have to learn memory layout, understand the stack, trace logic across just seas of raw data.
It's pure detective work.
It is. And Carlin also taught him how to format code professionally, using proper blanks, organizing with rows of stars, writing comments that actually mean something. This wasn't about making the code work. It was about making the code readable, maintainable, and understandable to other human beings.
That was the foundation of his professional career.
Absolutely. The habits you need to work reliably inside a team.
So if we synthesize this whole section, skill acquisition really happens in these stages.
Yeah.
First, theory connected to physical reality with the digicomply.
Then observation connected to deduction with the ECP-18.
And finally, technical skill connected to professional discipline with Jim Carlin. It's that personal, guided tutelage that provides the structure universities rarely can. The lesson is just so clear. School teaches the theory, but it can't teach the discipline, the practice, or the skill of being a craftsman.
And those things just require years of personal guided exposure.
Which leads us perfectly to the next big problem.
Right.
How do we industrialize the process of finding a Jim Carlin? I mean, if the self-teaching and these chance encounters are effective but totally inconsistent, the industry needs a formal, rigorous, repeatable structure.
And the source suggests we look to the gold standard for professional induction in a high-stakes field, the medical profession.
It's a powerful analogy.
It is. The medical profession is this centuries-old model of structured learning and quality control. They have a discipline of intense mentoring. It's standardized, it's regulated, because the stakes are literally life and death. Medical graduates get an excellent classroom education, but their transition to practice involves roughly equal amounts of classroom study and clinical activity.
Working side by side with experienced pros in hospitals.
And the structure is non-negotiable and it's long. After graduation, but before you can get a license, you have the internship, a mandatory year of supervised practice and training. The intern is just fully immersed, surrounded by role models and teachers, learning through intense, practical, on-the-job application.
And that's just the beginning.
Just the start. After the internship comes the residency, which lasts 3 to 5 years. This is more supervised practice where the resident gains confidence and specialized knowledge, but they're always under the continuous oversight of senior doctors.
And if they want to specialize even more.
They often need another 1 to 3 years in a fellowship. Only after this years-long, highly supervised gauntlet of practical experience are they finally deemed safe and competent enough to take their final exams and get board certified.
Because, as the source says, you cannot just throw meat into an operating room and expect a good outcome.
And that's the contrast that highlights with the source comes the insanity of software development. While software errors cause relatively few deaths, though, not zero, the financial stakes are just astronomical.
Companies lose enormous amounts of money from bugs, poor architecture, project failures.
All of which stems, in part, from inadequate training and a lack of professional discipline.
We're trusting civilization's critical infrastructure to developers who often have little to no formal, supervised practice. It really drives home the argument that the software industry is just wildly inaccurate, almost reckless in its approach.
The source calls it insane that companies will hire kids right out of school, form them into teams, and ask them to build the most critical systems.
The comparison that really stings is with the trades. Plumbers, painters, electricians.
Yeah.
They don't do this. Those fields have rigorous, structured, multi-year apprenticeships.
And the source suggests that companies hiring CS grads should invest more in training than McDonald's invests in its servers, which have these highly standardized, documented training processes. That really drives home the lack of respect for the craft itself.
It's a damning comparison.
It is. And given the level of societal trust we place in software, the source concludes that a reasonable period of training and supervised practice is not inappropriate. It's an essential requirement for professionalism.
I agree completely with the sentiment, I do. But let me push back a little here. This medical model sounds massively expensive and demanding. Master-level doctors are the most valuable people in the hospital, and they have to spend a ton of their time teaching and supervising.
Right.
Masters in software development are also the most valuable, most expensive employees. Is any company in this fast-paced tech world realistically going to pay their top architects and technical leads to spend half their time actively babysitting and technically reviewing interns instead of, shipping the product that makes money right now?
And that is the absolute core of the challenge. We are prioritizing short-term deliverables over long-term quality and stability. But the sources argue that the money you think you're saving on structured training is immediately lost to technical debt, to bugs, to project overruns. If you actually quantify the lifetime cost of a bad architecture written by an unsupervised junior, the cost of formal mentorship suddenly looks like a critical, necessary investment, not a luxury expense.
Okay, so if we accept that the investment is necessary, what does the structure actually look like? The sources propose the specific 3-tier software apprenticeship structure, drawing from medieval craft guilds.
Right. At the very top, you have the masters. These are the elder statesmen of the code base, the technical guardians.
So typically programmers with 10+ years of experience, they've led more than one big project successfully. Their role's comprehensive. They lead, they're designers, they're architects, and crucially, the source says they can code circles around everyone else without breaking a sweat.
And they often consciously choose to stay technical. They've declined management offers to stay hands-on. The company recognizes their unique authority by assigning them specific technical stewardship responsibilities. They set the standard. They are the role models.
Okay, next down are the journeymen.
These are your competent, trained, energetic pros, usually around 5 years of experience. They know current tech, they work well in teams, but they don't yet have that deep cross-system, cross-language experience that defines a master.
And their most critical role in this structure is what?
They are the designated teachers. They're supervised by the masters, sure, but their main focus is mentoring the next tier down. Their own work is still scrutinized until they gain full autonomy, but their job is to teach the apprentices the core professional disciplines and rituals.
So they're teaching the how-to, the design patterns, the disciplines of testing, how to do estimation.
Exactly. They instill the daily habits, test-driven development, refactoring, estimation techniques. These aren't just technical skills, they're professional commitments to quality.
Okay, let me push back on this journeyman role again, though. What if you have a brilliant coder, 5 years in, technically amazing, but they have zero patience and can't communicate to save their life? If we make them a teacher, aren't we just risking spreading bad habits or frustrating the apprentices? The medical field actually requires teaching skills for this kind of role.
That's a key point, and it's a structural element that has to be addressed. The source implies that becoming a journeyman isn't just about your technical skill. It's about demonstrating the ability to transmit that knowledge and those professional values. If someone is a terrible teacher, they might remain a senior developer, a highly valued one, but they wouldn't get the institutional authority of a journeyman, which carries that specific responsibility for teaching. So teaching ability itself becomes a critical professional metric.
Understood. Okay, and finally, at the bottom tier, we have the apprentices or interns.
Right at the start of their careers, they come in with zero autonomy.
They're closely supervised, doing simple tasks to help the journeyman. And the source really emphasizes one particular practice for this period.
Intensive pair programming.
And that's the key mechanism for transferring the discipline.
Precisely. That's where those fundamental values get created and reinforced in real time. You're watching the journeyman commit code only after writing a test. You're watching them refactor working code to make it clean. You're observing how they handle deadlines professionally. The apprenticeship should last about a year. At the end, if the journeyman recommend it, the masters interview the apprentice, review their work, and if they're accepted, they become a journeyman.
That whole system provides technical supervision at every single step. But if we look at how things work today,
Yeah?
how does the current structure differ from that?
It's almost the inverse. Today, new grads are supervised by young team leads who are supervised by project managers and so on up the chain. The core issue is that in most companies, that supervision is focused almost entirely on deliverables, on resource allocation, on project management metrics.
So it's managerial and administrative,
Right.
not pedagogical and technical.
Exactly. What's missing is that nonstop, intense focus on technical teaching, training, supervision, and code review. We're nurturing project managers and ticket closers, not technical craftsmen. And that responsibility, the source is adamant, must fall to the elders, the masters, and the senior staff who have the wisdom and experience.
Okay, so we've laid out the structure, the apprenticeship, and the historical need for this kind of mentoring. But a structure alone can't enforce discipline. You need an underlying mindset to sustain it all. And that brings us to the ultimate professional mindset required: craftsmanship.
Craftsmanship is the soul of the whole structure. It's the set of values that defines a professional beyond just their ability to make code compile.
The word itself, craftsman, it evokes quality, experience, skill, competence. How does the source specifically define a software craftsman in the context of the industry?
A craftsman is someone who works quickly, but, and this is critical, they never rush. They give reasonable estimates and they meet their commitments. They have the ethical backbone to know when to say no, but they also try incredibly hard to say yes. Fundamentally, a craftsman is a professional. They write code that not only works, but is maintainable, testable, and robust.
That idea of working quickly without rushing is so central.
Yeah.
It implies they're efficient because they don't make mistakes that create technical debt down the line, precisely because they stick to these rigorous disciplines.
Exactly. The novice rushes and creates more work for tomorrow. The craftsman might seem slower up front, but they deliver consistently and rarely create those huge, costly problems later on.
The source then takes this idea of craftsmanship and elevates it to something much more profound. It calls it a meme, not, the internet joke kind, but in the original cultural sense.
Right. Craftsmanship is described as a contagious mindset, a kind of mental virus. This meme contains all the values, disciplines, techniques, attitudes, and answers you need for professional success. It's exchanged between peers, and most importantly, it's taught by elders through observation and emulation.
What's so fascinating, and frankly pretty counterintuitive for an engineering discipline, is what the source says about how this meme gets adopted. You'd think that in a rational field, data, case studies proving TDD saves money would be what convinces people.
But the source argues the exact opposite. You absolutely cannot convince people to be craftsmen with arguments or data. The acceptance of this meme is fundamentally not a rational decision. It's an emotional one.
An emotional one. It's described as a very human thing.
It is. Logical arguments just don't work. Data is basically useless in changing the core professional identity of a developer.
But why? In engineering, we value rationality above almost everything else.
Because adopting craftsmanship requires a kind of professional patience that often goes against short-term pressures. I mean, think about something like TDD. The first time an apprentice tries it, it feels slow. Writing the test first feels like wasted time. Spending hours refactoring code that already works feels unnecessary.
So they have to commit to it based on trust.
Exactly. Trust in the experienced journeyman or master who embodies that discipline, who shows them that this counterintuitive process pays off in the long run. It's a leap of faith at first, and it's driven by respect for the role model, not by a business case. The apprentice basically says, the master does it this way, so this must be how professionals behave.
It's a total shift in professional identity, recognizing that being a craftsman means holding yourself to a higher standard, even when the immediate pressure is just to ship something.
And that shift requires an emotional connection and trust in the authority of the elder. Data just rarely provides that.
That places an even heavier burden on the experienced developers then. If it's emotional, how do we propagate this necessary mental virus effectively across the whole industry?
The key, according to the sources, is simple. You have to make it observable. You have to actively perform the role. You become a craftsman first, and then you let your craftsmanship show visibly in everything you do. The meme spreads through osmosis and observation.
So the masters and journeymen can't just delegate and disappear into meetings. They have to be visibly demonstrating quick, quality work, meticulous discipline, and ethical commitment in their daily coding. When that apprentice sits next to a journeyman during pair programming, they aren't just learning syntax.
They're absorbing a professional way of being. And that's the whole synthesis of the argument. School teaches the theory how the machine works in the abstract, but it cannot teach the practical discipline, the meticulous habits, or the professional mindset of a craftsman. Those are acquired through intense, visible, years-long tutelage, and the industry just cannot afford to leave this critical learning to chance, waiting for an accidental mentor like Jim Carlin to show up. We have to formalize it.
It's really time for experienced professionals across the software industry to accept the inevitable, guiding the next generation of developers to true professional maturity. That's our responsibility.
Right.
It's not the university's. We need to implement a formal, rigorous, and technically focused program of apprenticeship, internship, and long-term technical guidance, using that medical model as a blueprint.
If we fail to do this, if we fail to formalize this transmission of technical discipline and the craftsmanship meme, we're just guaranteeing the continued financial bleeding from poor quality, from technical debt, from system failures. We're risking civilization's critical infrastructure by trusting it to practitioners who have the theory, but lack the vital practical habits of the professional craftsman.
And that brings us to our final provocative thought for you to carry forward. If the acceptance of the craftsmanship meme is fundamentally emotional, and if it requires an observable role model to be transferred, what specific visible behaviors or actions must today's masters and journeymen be demonstrating right now beyond just committing clean code to actively ensure the future quality of software? The job, according to our sources, is not just to produce quality work, but to visibly perform the role of a craftsman every single day, allowing the next generation to observe and emotionally emulate that professional discipline. Think about what you are making observable in your own work and in your teams.